Okay, thank you all for coming out and seeing the first STEM series lecture of the school year. There are several people I'd like to thank. First of all, I'd like to thank Sharon Pericelli from the STEM Center, who's seated in the back there. I'd also like to thank some of my colleagues, some of whom are here, Bruce McCormick and Avinash Pandey of Cognimem, and then some of my fellow department colleagues, Dr. Clevenger, who you've met, and Du Zhang and Sui Zhang, who I've worked with quite a lot. My grad students, some of whom are here, you'll meet at least one of them, Adam Ruggles, that put their heart and soul into this research. Let's see, Public Affairs, Gloria Moraga is here, and Creative Services, the producer, Jeff Madlicott, is in the back. All right, the quest for an artificial brain, that's a pretty lofty sounding topic. Actually, people in my field don't call them artificial brains. I just thought that would sound kind of cool. Neural networks is really the correct term. And so let's start by asking you this question. What is this? All right, so I heard a bunch of people say it's a cat, and pretty much everyone says that's a cat. But how do you know that that's a cat? That's a cat. That's my cat. But you all said it was a cat. I doubt if you've ever seen a cat look like that before. It's the wrong color. The feet are all wrong. There's no fur. The mouth is wrong. There's no tail. And yet you all said it was a cat. That was pretty, if you think about what your brain had to do to identify that as a cat, that's pretty astounding. And we can sort of categorize a couple of things that led you to say it was a cat. One of them is that when you were young, you learned what a cat was. You learned what a cat was. So there was probably a process that involved your parents and showing you pictures of cats or having a cat around. And so you learned a lot of things, including what's a cat. But you didn't just learn how to identify particular cats. You did what we call generalize, to where you're not only learning particular cats, but you're learning the concept of a cat so deeply that you can identify all of these very, very different objects, and you would quickly identify them all as cats, not as dogs, not as platypuses, or any of the other animals that you know. You identify them all as cats. So remember these two terms, learn and generalize, because there's a lot of fantastic things that the brain does. But we're going to focus on those two things that the brain does today. So what is the brain? Well, I have to confess I'm not a neuroscientist. And so there's a lot that I don't know about the brain. There's a lot that everybody doesn't know about the brain. The brain is a pretty fantastic thing. And so let's say a few things about the brain. First of all, it has a lot of neurons in it. You've probably heard that term, neurons. It has about 100 billion of them. That's the human brain. It has about 100 billion neurons and about a quadrillion synapses. A synapse is a connection between neurons. Each neuron connects with approximately 7,000 neighboring neurons. That's a lot of connections and a lot of neurons. What can we say about the neurons? Well, the neurons are really complex, and each neuron is a very, very complex little engine. It's an electrochemical device, and it sends signals to the other neurons that it's connected to, and it receives signals from its neighboring neurons. And I'll tell you, there's so much complexity in the way the neuron works that is outside of my area of knowledge. What people in computer science or artificial intelligence are interested in is sort of the function of the neuron. What is its basic function, and can we model that basic function? Because it's too complex to try to model the entire, every little step that the neuron does to achieve that function. But for the most part, neurons seem to have an all or nothing binary type of behavior. And we usually say that they fire or that they don't fire. They don't partly fire, most of them generally. They don't fire a little bit or a lot. They either fire fully or they don't fire. So any given point in time, a neuron is, the importance of its function is that it is in one state or the other. It's either fired or it's not fired. And that all or nothing behavior is awfully reminiscent of the bits in a computer that are either ones or zeros. And so right at the very beginning of computer science, when computers were first being built, people saw this analogy because people have known about this sort of all or nothing behavior of neurons for quite a while. And they thought, wow, if the neuron is sort of on or off, all the bits in the computer are either on or off. Maybe we can shape the computer to do what brain does. That's the idea. All right. So if we want to do that, how do we suppose knowledge is organized in all these neurons in our brain? Well, that's like a $64,000 question. Nobody knows. It's quite complicated, and the trouble is if you go digging around in there to try to figure it out, the unfortunate person will probably stop knowing things, and then you won't be able to get your answer. But there is evidence that, although we don't know how it's organized, we know that it's very distributed. So what does that word distributed mean? It means that the neurons are not very specialized, most of them, and they're shared by a lot of different memories. So if you smell a flower, that'll cause a whole bunch of your neurons to fire. If you hear a particular tune, that'll also cause a bunch of neurons to fire, and some of the same neurons that fired when you smelled the flower also fired when you remembered a particular tune. And so it's all those different combinations of ways that neurons can fire that give rise to the huge number of things that you can remember. At least that's the way it seems. All right, so back to that first function that was so fascinating that the brain could do, which is learn. How does learning happen in the brain? Well, that it seems that scientists know a little bit more about, at least know some of the mechanisms that happen when you're learning something, or more appropriately when a young child or an animal is learning something. And that is that as you're learning things, certain structural changes actually happen in your brain, in the neurons. What sort of structural changes? So there are a lot of really complicated ones, but I'm going to distill it down to the basics. When you're really young, a lot of learning involves growing new neurons. In fact, you grow new neurons when you're an infant. You grow new neurons at a staggering rate. It's like billions a day or something like that. Really, really fast. But as you get older, you actually start losing neurons, as many of us know. But you can still keep learning. And how does that learning happen? Most of it is either new links being established between existing neurons, or the strengths of the connections between the neurons can be adjusted. In other words, the resistivity along some of the connections can either be made greater or less. That's an important concept, that last one. Well, I'll tell you how learning does not happen. If you want to teach your child how to tell what's a cat, you don't open your child's cranium and wire up the neurons. with tweezers. The process of learning and of making those changes happens automatically. It's part of response to stimulus, to input. And that's another important concept. Because if we're going to build an artificial brain and we want it to learn, we don't want to have to wire it up ourselves any more than we would want to wire up our kids' brains by hand. Let's take a look again a little bit more closely at the neuron. And again, this is, if there's any biologists in the house, I don't mean to offend you by this oversimplification. But we look just from a functional point of view. What does the neuron do? So suppose this little green circle is a neuron, and these incoming arrows are neighboring, are synapses, attachments from neighboring neurons. So some input stimulus from some of the neurons, some of the neighboring neurons fire, and some don't fire. So what's going to determine whether or not our neuron here should fire? Well, it all comes down to whether or not the incoming pressure from neighboring neurons exceeds some threshold. If enough of the neighbors fire that it exceeds the threshold, then our neuron will also fire. And if that happens, then it will in turn exert pressure on other neurons, and some of which may fire and some of which may not. So that's a really, really simple look at what a neuron does. It's all or nothing, meaning that if this neuron doesn't get enough stimulus from its neighbors, it won't just fire a little bit, it simply won't fire at all. It'll just sit there waiting until it gets enough stimulus to fire. Okay? Now it turns out that's pretty darn simple. And that's simple enough that we can model it in a computer. So here would be a way of modeling it in a computer. So this is what we would call an artificial neuron. It's not actually built in hardware in this case. It's in software, so it's in a computer program. All right, how would it work? All right, suppose in this case our artificial neuron is this square, this green square, and the inputs are coming from other artificial neurons. Now, if we model the fire and not fire as 1 or 0, that means those inputs are either going to be 1s or 0s. For instance, if I1 is a neuron and it fired, then I1 would be a 1. And if I2 was a neuron that didn't fire, I2 would be a 0, and so on. So imagine that. We're labeling the inputs coming from other artificial neurons, and they're 1s or 0s. Now, here's where we simulate how the connections can have different strengths. Remember I said how during learning, the connections between neurons can change their resistivity so that some pathways are stronger, pass the signals more strongly than others. We simulate that using weights assigned to each of the connections. And we'll label those with W for weights. All right, so the W1 tells, if that's a big number, that means the strength between neuron I1 and our neuron is strong. If it's a small number, that means that the connection is weak. And those numbers typically could even be negative. If we wanted it to have a negative correlation, they can be negative. Okay, here comes the first and only piece of math in the talk. Now, most of you, I think, have some technical background, so this won't throw you. But I think any of you can follow this one. Okay, the neuron computes what we call a weighted sum. So it takes that I1, multiplies it by W1, then it takes I2, multiplies it by W2, then I3 multiplies it by W3. Adds those up together, that's a weighted sum. So we're adding up the inputs I1, I2, and I3, but they're weighted according to how strongly they're connected. So if the connection between I2 and our neuron was very, very strong, then if I2 fires, then there'll be a lot of pressure coming in because the weight, too, would be very big. If on the other hand, the connection between I3 and our neuron was very small and W3 was very small, then I3's influence on our neuron would be very slight, and by itself, it wouldn't exert a lot of pressure. And as we're going to see in our model, those weights are what we can adjust when we want our artificial network to learn. All right, so after computing that weighted sum, if that sum is big enough, if it is bigger than some threshold, and remember that's what determines whether a neuron fires, if the incoming pressure is enough that it causes the neuron to fire, then our neuron will fire. So we check to see if that sum is greater than some threshold, and that threshold in most artificial neural networks is some constant number like 0 or 1. Turns out it doesn't really matter what it is as long as there is a threshold. Then, since ours is a neuron, if its input pressure is bigger than the threshold, then we want it to fire, meaning output a 1. And if there wasn't enough incoming pressure, the summation would be small, and we would just output a 0. So here's the behavior. We would output either a 0 or 1, and that would be sent to other artificial neurons with their own incoming weights on their connections. That's just one neuron, one artificial neuron modeled in software. To make a neural network, we have to hook a whole bunch of these together. All right, again, we would typically do this in computer software, and there's a fancy name for a neural network that looks like this with the behavior I just described. It's often called a multi-layer perceptron. So you can impress your friends with that term. I'm just going to call it a neural network. So in this picture, all of those circles are the artificial neurons, and as you can see, they're highly connected to neighboring neurons, and every one of those connections has a W or a weight that can be adjusted. And it's adjusting those weights is how it would learn. All right, so that's a very simple neural network model. All right. So how does one of these neural networks learn? How do we usually refer to training the neural network. And so I'm going to show you this, what we would call an algorithm. I'm going to show it to you more than once. So if you don't fully get it the first time, that's okay. We're going to revisit it a little bit later. This is a common method of training neural networks. There are other methods of training neural networks. This one is called supervised learning. In supervised learning, we have to have some training, what's called a training data set. A training data set would be like, suppose you wanted to teach your infant child about animals, and so you got a picture book of animals. And you showed the pictures to your child and told them, okay, this one's a cat, this one's a dog, ones that you already know the answer to. Okay, that's training material there. That's what we call the training set. You've got to come up with training data first. Then we don't know what the weights should be to learn that stuff. That would be complicated to try to go in by hand and figure those weights. So we just start by randomizing the weights. Just assign random numbers for each of them. Computers are good at coming up with random numbers, so that part's easy. Sometimes they come up with random numbers when we don't want them to, as we all know. But in any case, we assign them all to random values. Then what we do is we pull out one of the training cases. So if we're trying to teach them animals, we would say, okay, here's a picture of a horse. Now, we show the neural network the input and have it tell us what it thinks it is. Well, if the weights are all random, the answer is probably going to be random too. Right at the beginning, we show it a horse, it's probably going to say that's a fish. Something like that. It will likely be wrong. Okay, that's expected. The next step says, was it correct? Well, chances are at the beginning it won't be correct. So then we have to modify the weights to make it so that the next time on that same input, the answer will be closer to correct. And then we go grab another training case. And we keep doing that over and over and over again. Over time, it's going to start answering some of them right. And when it does, then we have to ask ourselves, do we need to keep training? Well, that depends. If it answers all of them right, if it answers the entire training set right, then we're done. We're done training. It's learned the entire training set. So there at the bottom, when we say, okay, was it right for that particular case? If so, then we have to ask, are we done? I mean, did it get all of them right? If no, we have to go back and keep going until it gets all of them right, and then we say it's trained. Okay, if you're not quite sure, here's a picture. Let's say we have our neural net that we saw from before, and let's say we arbitrarily assign the first output that if that top rightmost neuron fires, that means cat, and if the one on the lower right fires, that means dog. All right, so we show it a cat. At the beginning, the weights are all random, so who knows what it's going to say. Maybe it'll say it's a dog. Okay, that's the wrong answer. All right, so we would have to adjust the weights until finally, when we show it the cat, it actually responds with cat. All right, and when we show it the dog, it might say that's a cat for a while, until finally we get the behavior that it properly replies dog when it's a dog, a cat when it's a cat. All right, so in this case, it's a very, very small training set. We only have 2 pictures. Usually the training sets would be much bigger, and training would take a long time. Okay? I did a bunch of hand waving back there that when I said adjust the weights. How do we do that? All right. How to do that? There are a lot of different methods, but I'll tell you that was the hardest part about neural networks, neural network research. For about 40 years, people tried to find a way to reliably adjust the weights in that process of supervised learning. It was like a holy grail in computer science to come up with a mechanism for adjusting the weights that would reliably lead you to actually learning a training set. And it was in the early 80s when that was published, and it was considered an incredible breakthrough in computer science. And the algorithm that was published was called backpropagation. And I'm not going to put that math up here because that math is intimidating to me. But it works, and shortly thereafter, people started discovering other ways of training those weights or adjusting those weights as well. Here's just 4 methods. We have students here researching backpropagation and particle swarm optimization. There's other methods, simulated annealing. There's a lot of different ways out there for adjusting the weights in a neural network. And so you'll just, for this talk, have to take it on faith that it is possible to do that, gradually adjust the weights over time by showing it training cases over and over and over again until it finally learns your training set. All right, so we've talked about how learning happens. Learning happens by adjusting the weights in response to the training data. And that's pretty similar in a very crude way to what happens in our brains. As you are told, no, that's wrong, it's this, there are structural changes in the connections and synapses in your neurons that are loosely modeled by that weight adjustment. But what about this generalized? I told you at the beginning that the 2 aspects of the brain that we were really going to talk about here was learning and generalizing. So what about this generalized piece of the puzzle? Well, if we go back to this algorithm here, anybody that knows anything about algorithms would look at this and realize I left off a branch. I have that question on the lower left that says done. If we're not, go up and input another training case. But what if I don't have a yes branch out of there? So when it's all done, then what? When we're done training, well, think about it. When we're done training, that's when we want to see if it has what? Generalized, right. Because If it has generalized, that means that we could show it other dogs and cats. And if it's generalized, it will correctly identify them. Maybe show it this cat or this dog. That cat and that dog were not in the training set. If generalization occurs, then it will correctly identify similar examples that it was not trained on, examples it had not seen before. And neural networks, if you have a sufficient training set, commonly are observed to generalize. That's usually the goal, is to train something well enough that you can then put it in the field and it'll work in other cases. There's another cat. All right, so to complete this, I need to check generalization and see if it is able to correctly identify other cases that were not in the training data set. Well, that means I need to have a test data set with different inputs and different expected outputs so that I can gauge whether it generalized. Because if I train it on 50 different cases, but I've set aside 10 cases to check afterwards, and after training, I show it those, and it gets those right too, then I might be pretty confident that, that it's learned something. And it's not just memorized those particular inputs, but it's actually learned some concept. So at the beginning, actually, we need to build a training set and a testing set. I only use the training set during training, and I use the test data set at the very end just to check and see if it was able to generalize. All right, so at the end of the training is when we check to see if generalization occurred. Turns out that this kind of a method has a lot of applications. Here are just a few of them. Optical character recognition. When you write in handwriting, having a computer be able to pick out the letters that you've written is a generalization problem because everybody has different handwriting. There's a lot of robotics. You can go online and look up and Google stock trading neural networks, and you'll find a lot of products you can buy to help you predict the prices of stocks that will actually learn to predict stock prices using a neural network. And these are actual products that you can buy. They're used a lot in games. Some games can actually learn your behavior when you're playing against the game and therefore become a stronger opponent. They're used in medical diagnosis, email spam detecting. There are at least 5 courses here at Sac State in which neural networks are utilized. 3 of them in the computer science department, 1 in ME and 1 in business. And there are also many professors and students, researchers here, using neural networks in these and in other departments as well. One of the things, if you're at all interested in studying neural networks, say here at Sac State or anywhere, I like to tell my students that, well, one of the advantages of going to college is that you also get exposed to a liberal arts education too, and so you get a chance in some of your philosophy classes to study some of the weighty questions that have, like why are we here, and what is consciousness, and things like that you study in philosophy classes. Well, I like to tell my students that some of those really age-old human questions we tackle in artificial intelligence class, and we really tackle it. We don't just talk about it. We actually model it and run it on the computer and see if it's actually right. So it's an exciting field. It's almost like, to me, artificial intelligence, and particularly studying and modeling the brain, is almost like a final frontier of computing because it's such a rich challenge and such a complex thing to try to do. There's way too much examples of research on the campus here in neural networks to list it all. I thought I'd just list a few of my own students that have used neural networks in their research while they were students here. I had a student, Michael Darter, who implemented a snowplow assisted driving using a neural network so that snowplow could run even during a whiteout. Here was an example of some undergraduate work where student Tim Bender used a neural network to divide a very hard problem for regression into pieces and solve it by divide and conquer. Very recently, one of my master's students, Amaya Deo, trained a neural network to detect when a medical monitoring system was about to fail, and that was important to be able to warn system folks so they could try to stop that from happening, because you don't want medical systems to crash that can be life-threatening. And one that we'll talk a little bit more here in a minute, stereoscopic tracking. One of the things I'm most excited about is that there's a local company called Cognimem in Folsom, and they actually develop a neural network on a chip. Is anyone from Cognimem here? Raise your hand. Oh, Avinash. Great. Hi. One of the hard things about neural networks is if you think about it for a minute, you think, well, 100 billion neurons, we've got computers we could have 100 billion bits in the computer. So why can't we achieve the brain? Well, the problem is that in our brains, it's possible for all those neurons to fire simultaneously. But it's not possible to go through all the bits in your computer and have them all flip simultaneously, or flip or do their own computation simultaneously. We don't have that kind of parallelism. Everything goes through the CPU, and so all the processing is serial. That's really, really slow. Even though the artificial neurons these days are faster than the real neurons, the assemblage is way, way slower. In fact, 2 years ago, there was a simulation by this Neurosciences Institute in San Diego where they simply tried to replicate 1 second of mouse brain activity. Just run the calculation, they modeled the number of neurons in a mouse brain and say, if we just have them fire for 1 second, how can we actually do that amount of computation? And it took a supercomputer 2 months. That's a mouse brain which is 1/10 the size of our brain and has less connectivity as well. So just the raw computing power, because of the parallelism, just gives the brain this incredible computing strength. What Cognimem is doing is they're actually achieving that kind of parallelism by putting the neurons on a chip and using a highly parallel architecture. And so they're able to actually achieve some speeds that we could not do in software. By the way, they don't use them. The one what was the one I told you before was the previous model? I had a fancy name for it. Did anybody remember it? Yeah. Oh, some of you remembered it. That's good. Okay, those of you who remembered it can impress your friends. The multi-layer perceptron. They aren't using a multi-layer perceptron. They're using a different model, which I haven't described to you, but it's also a neural network called a radial basis function neural network. Each chip has about 1,000 neurons on it. It can actually learn a pattern in 2 microseconds and recognize a pattern in 3 microseconds. That's pretty fast. That's faster than we can do in software. And you can put them together into various configurations. They've got some configurations that have up to 1 million neurons. 1 million neurons, that's tiny compared to our brain, which is in the hundreds of billions. But it's bigger than the ones we have in software. They also configure them onto different boards. Here's a board they make called a V1KU. And this board is pretty cool because it has a camera on. Oh, the dollar is not the price, unfortunately. That's just to give you an idea of how its size. You can see on the left-hand side, it's a CM1K. It's pointing to where the neural net chip is. It also has a camera on it that's integrated and a USB port so you can hook it up to a computer or other devices. It's got a little processor on it and a memory chip, what's called a field programmable gate array, where you can actually program it. And so that particular device, we actually have two of them up here. They were very nice in letting us use some of them. The V1KU has been used in a lot of real-world applications. One of the most interesting ones, well, the first one, locating glass imperfections. You can see here a row of these V1KUs. There's a Japanese company that uses the V1KUs to detect imperfections in glass as they're manufacturing it. Very interesting application. The picture on the upper right, in the Nordic fishing boats, where fish are getting packed into bins, and they want to make sure that the bins are being packed properly. And yet it's very extreme conditions, very, very cold, or very, very windy, or very, very wet. And sometimes laptops and people don't survive so well there. And so this enables them to make little special and enclosed devices that can hold up to just about anything. We're using them here for binocular vision. What's binocular vision? Well, we have two eyes. There's a reason we have two eyes. That's so when something walks by, when our eyes look at it, our brain, in another one of its amazing things that it can do, our brain knows how far apart our eyes are. It knows the angles that our eyes are when we're trained on something, and it can do the math and tell us how far away something is. So depth perception is really your brain doing a geometry problem. We'd like to have a system that can do binocular tracking in real time. Learn something and then track it with depth perception. And the V1KU gives us a good platform from this. Now you might say, well, my video game can do this. If you have a Microsoft Kinect with an Xbox, that can actually do stereoscopic tracking too. It's quite a clever device. It uses a totally different approach. It uses what's called structured light, in which it throws a beam of infrared light on the subject, and you can't see it, but it has a sensor, and it can see the light that it's throwing, and it looks for perturbations in the light. That means that it's able to track things in the room that are close to it. But it's pretty much limited to that. It's limited to things it can wrap its light around. So it wouldn't be able, for instance, to track something very far away, say out of a helicopter, or it wouldn't be able to track something on a screen because it would be just flat on a screen. So if you want to have a general purpose 3D tracking system, that turns out to be hard, where you just have a couple of cameras and it sees something and tracks it. That's really hard because it's computational intensive. The graphics involves a lot of math and a lot of computing. There's background images. If something is behind the object, it can fool your tracking system. Lighting variations. Anyway, it's a hard problem, a known hard problem. And so we're trying to do this using a pair of V1KUs, where the cameras on the V1KUs are the eyes, and the neural nets on the V1KUs are where we learn the patterns to track. The V1KU is pretty well suited to that. So we attach the V1KUs to a couple of motors so that as an object moves, the motor can move with it. And so we attach the little motors to a controller. We have a laptop connected to the V1KUs and to the servos. And we have a program that can turn the recognition and learning into tracking. And to do that means that as an object moves, we have to move the servo to where the V1KU tells us the object has moved, so that the servos always keep the object in the center of field of both cameras, and then we can do the triangulation to find out the distance and therefore the actual location in 3D space. That's the idea. So we have a prototype we've been developing, and It works on some cases pretty well, and in other cases it has difficulty. And so I have one of my grad students here who developed this version, the most recent version, as part of his master's project, and that's Adam Ruggles. And perhaps Adam can come up and we can try to show it to you. It's a little hit and miss up here, and we're also having some challenges getting things to show up on the projector. So if you'll bear with us for a couple of minutes. I think I have to get the hang up, right? Hang out. Ordinarily, we would hook up his computer to the projector, but you know how those Macs are? He's a Mac guy, I'm a PC guy. So which one do I do? Hang out?
Yeah.
So we figured out a workaround. We're actually using what's called Google Hangout to get his screen on my screen because my screen's on the projector. Comes out pretty low tech, but it sort of works. There's Adam. Okay, unfortunately, it's pretty small, but, well, it's talking back to me. While Adam is setting this up, oh, we're getting a nasty echo on this. I'm going to try to explain to you what we have here. You know what? I'm going to turn the volume down on my computer because that echo is going to drive us crazy. Okay, that's better. All right, so what we have is we have a device that has two of these V1KUs. So in each of these is a camera and a neural net. And they're mounted on a servo motor. Each of them is on a servo motor. And so they can turn just like our eyes turn. And Adam is running a program that you can use to tell one of the V1KUs to see something and learn it. And it stores that in some neural connections in its neural net chip. We can copy that knowledge to the other one, and then we can tell it to track, and it will attempt to keep that object that it's just learned centered by moving the servos to keep it centered. And if it works, it will also tell you the distance that it thinks it is away, and it'll show you the triangulation that it's doing. This really wouldn't be possible, at least at the speed at which we're learning, if it weren't for the speed of the CM1K neural net chip. So we need something to track. So we can try a roll of duct tape. He's a little bit better at using the software. So, if I stand out here, yeah, with the duct, oops, what happened here? With the duct tape, you can see I'm holding the duct tape, and he is mostly black here. He's moved the little square box around the duct tape and told it to learn. And you notice that sometimes it has a little REC above it. That means it recognized it. And so now you're training the other one now? So now he's training the other one. lighting in here is a little not too great. It thinks my chin is the duct tape right now. It's not too far off. So actually what he's doing, he's having it learn the duct tape, and then when it sees other things and thinks that those are the duct tape, he's telling it to unlearn those things. The radial basis function neural network, that model is good for both learning and unlearning. So sometimes a combination of learning and unlearning. And we're still working on these algorithms. Right now he's having to do a lot of the learning and unlearning by hand, whereas in the future we're hoping to make some of that automated so that it'll just learn an object and then look everywhere else and automatically unlearn other things. But we still have a lot of work to do. And we really don't know what to expect when we actually ask it to track this. So it could track it pretty well. It could crash and burn. I'm not sure. Mainly we want to just show you what we're working on. So when you see it switch from being one window to being two windows, then you're actually looking through both of the cameras. And if the duct tape is in the middle of both of the lenses, that means it's tracking it. At which point I'll try moving around and see if it succeeds in tracking. So it probably would help if I were over here. We're almost out of time, so we'll,
normally it takes a good 30 minutes to run some problems. So.
The way we have it set up now, it's still obviously in the prototype stages. So if you actually try to tell it to track now, will it? There we go.
Move it right over in this dark spot right here.
Over there. All right. Yeah, okay. Recognizing it. We want to. All right. So it actually has the duct tape in the center. Now, okay, cross your fingers. Oh. Did we get a crash? Oh, it's back. All right.
It's being really slow. It might actually be Google.
It might be because of Google Hangout, yeah. We have that extra layer on top of it so that it would come up on the screen. That's actually tracking it here.
Yeah, then it stops. It's tracking good.
Yeah, it is a little stop-start thing because of the Google Hangout. Yeah, I got to move in and out here. All right, so okay, I just can. Okay, it's managed to find one of them. The other one has gone a little cross-eyed. Oh, there we go. The distance is in inches, yeah.
The distance actually doesn't need a unit of measurement. We can specify whatever we want.
That's true.
But right now, the units we're using is the distance between these two inches. So if you change that to centimeters, it will go into centimeters.
Okay, well, thanks a lot, Adam. And so, yeah, any questions? Yes? Okay, yeah, the question is this motion tracking or object tracking, and actually we're doing a little of both because the V1KUs are doing object recognition and we're trying to move it to where it finds the object. But we've actually got in there the structure for it to, if something momentarily blocks the image and it's moving, that it will actually keep moving that way. And we use a device called a mathematical construct called a Kalman filter. Actually, Adam thought that idea up, to use the Kalman filter to predict where it's going to come next. So there's some motion tracking too. And there was a question over here. I think you were next. Yeah, if we do it in a really sterile environment, it actually tracks really well. Like perfect lighting, real even, and a very clean background, it tracks really great. But I don't know, that's not really very interesting. We're trying to get it to work well in cases like this, where it's more anything. And so, yeah, that's difficult. But yeah, in a real sterile environment, it does great. That's just less practical, because most of the world isn't very sterile. Question over here.
Is that learning cycle that you're going through on that system, is it like what you described, where you assign some random weights to the node and then check if it's the right answer and reweight?
Okay, so the question was, is the training that's used in the V1KU the same as I described for the multi-layer perceptron? And the answer to that actually is not exactly. The radial basis neural network has a little bit different learning mechanism, and the function of the neurons is a little bit different than in the multi-layer perceptron. And the neurons are a little bit more specialized. They define what are called regions of influence. And as you learn something, you're expanding certain neurons' region of influence and reducing other neurons' region of influence. So it is actually quite a different model, but the connectivity is very similar. The connectivity of the neural net is very similar. I debated whether to actually show you a radial basis function architecture too, and I just decided there wasn't enough time. So these are all things, by the way, if you go on Google, you can find tons of information about all this stuff. Yeah, any other questions? Yes?
Is there like industry standards that's developing?
Industry standards for neural networks, that's really interesting. I don't know of any. They're like an interface standard for it. Yeah, that's a really interesting question. And I'm a little bit surprised myself to say that I don't know of any industry standards for neural nets. Do you know of any, Adam?
No, I know some libraries that are coming out.
Oh, that's true. Yeah, there are some. That's right. There are some libraries that are available for various programming languages that offer, and so in that sense, you would have for certain languages typical ways that you would call neural net functions if you wanted to use the standard libraries. That's not really an industry standard, but when a library becomes popular, then it becomes used, in a lot of different products. So could it tell the difference between a regular cat and a cartoon cat? It all depends how you train it. If you specifically wanted it to learn to tell the difference between a real cat and a drawing of a cat, you would have to train it, have a whole training set with a bunch of pictures of real cats and a bunch of drawings of cats, and have the expected output of the real cats be one output, and of the drawings of cats be another output, and hope that it generalizes on that. So it's kind of your call what you want to train it on. Yeah. Yes. Oh, that's a fantastic question. The question was, is there a connection between the number of neurons you need and the complexity of the task? That's absolutely true. In fact, what held up this research for a long time is that early on, even back in I think the 60s, they had a training algorithm if your neuron was only one layer of neurons deep. They had a proven reliable training method. But if you do the math on that, then on what you're computing with those weighted sums, it turns out that all you're doing is drawing lines, and so you're only learning a type of function that's called linearly separable functions, which that's like the class of uninteresting functions. And so anytime, to get interesting, you have to have layers of neurons, like our brain is neuron after neuron after neuron. And indeed, there is a computational power that the neural network has. And if you are asking it to learn to distinguish, make lots of fine distinguishing between details, then yes, indeed, you need to have more computational power. And therefore, it will take longer to train too, if it's all done in software. That was kind of one of the advantages of the radio basis function networks in the chips, is that with that model, it actually can do more of it in parallel. And so when he puts the square around something and says learn, okay, it's actually learning that really fast. Now, it's still at the development stages because it's also generalized that a little bit too much, and it thinks other things are that too, and so then we have to do unlearning. But to answer your question, yes. The interesting corollary to that question is that it seems that if you learn something with just enough neurons but not excess neurons, in some cases it will generalize better because the neurons aren't able to be too specialized and it's having to distribute them. So sometimes people who are using the neural network try to find out how big to make it without making it any bigger. And right now it's still more art than science. Yes, Randy. No, oh, the triangulation? No, that's just done in the C# program. That's true. That's true. Our brain does the triangulation, and in this case, the brain is not doing the triangulation. You're right. Yeah. In fact, that's usually the case. I mean, these neural networks are so tiny compared to our brains that usually they are trained to be a particular subsystem of a larger system. It's not like in a typical industrial setting where a neural net is being used for some task. It's not always the case where the neural net's doing the whole thing. It's doing some piece of it that it's well suited for.
So when you say that our brains are solving math problems, like visually, do you understand that to be metaphorical or?
Yeah, I don't really know if it's actually if you were to actually trace the neural firing, if that would actually correspond to the geometry problem. You're right. I meant that metaphorically. Yes. That's the end effect. How it's doing it out, nobody knows. Fantastic questions. Yes? To construct this, let's see. The V1KUs, they gave them to us for free, so that was free. If these are, I think they're about $1,000 each right now. The servo motors, what are these about? $5 each. There's 4 of them here. The harness, Adam had fabricated the harness, was about $35. So all the expense was in the V1KU chips. Yeah. Right. Well, I could use them to learn more things. So you actually, this only is, our software that we're showing you here is only designed to learn one thing. But you can have, I think, up to like 1,000 categories that it learns, or it's probably more than that, I don't remember. But so you could have it learn several objects, and when it recognizes an object, it'll tell you which category that object is in. That's the typical use for this chip for using more neurons, is to learn more categories and to learn them more specifically. In some cases, it takes more than one neuron. I mean, it usually takes a lot of neurons. In fact, I have a video on my website showing an earlier prototype of this learning a smiley face. And it takes something like 50 neurons in the radio basis architecture to get a pretty good handle on that smiley face, and then it tracks it pretty well. So that's usually, in this case, what the extra neurons are for. Yes?
Given that the neurons either fire or don't fire, so would you generalize, would you say that the brain is analog or digital?
So is the brain analog or digital? That'd be an interesting question to ask a neuroscientist, wouldn't it? But it's definitely analog processes going on in there. Are the computations digital? If this model is correct, then you could say that the functional the functionality of the brain is as a digital computation device. But I don't think anybody really knows the answer to that question. It's not yet. Uh-huh. Right. Right. Yeah, the question is, this doesn't seem to approach the creativity of the brain, and that's what, yeah, that's some really higher order thinking that our brains can do, and yeah, the neural networks are not really at that point. There are a lot of artificial intelligence researchers that are working on creative applications of this and other AI methods related to music. Music is a pretty hot topic in AI. There have been people who have used some artificial intelligence techniques to have the computer propose completions of great unfinished symphonies, for instance. So that's an application. But right now, we're pretty happy if it can track a coffee cup. But yeah, that's what I mean by final frontier. I mean, AI there's so much possibility and so much unknown. And the more you study AI, the more awestruck you are by the brain. Yeah, I mean, some of that stuff we don't even bother to think about the whole idea of consciousness. I mean, if we had a big enough neural network and it actually seemed to start be creative, would it be self-aware? Would it be conscious? Gosh, I don't know. Yes, John.
So one of the interesting talk about the neural networks is this generalization.
Right.
You guys done experiments to see if once you learn the roll of duct tape, that won't replicate, or you've done generalization tests with it?
Yeah, well, actually, in the case of tracking, we were fighting a little bit with the generalization because it was finding little circles in other places and saying, oh, there's the duct tape. In fact, with tracking, we kind of want a little less generalization. But yeah, there have been a lot of research in terms of the generalization, and there's a lot of interesting things that people have observed with trained neural networks where maybe you train it to distinguish between different types of fruit. And people have studied, for instance, okay, let's say we remove a couple of the neurons, actually damage the brain, then what happens then to its recognition? And that distributed nature of the knowledge that is believed to be the case inside of our brain, that gives rise, we think, to the generalization, also gives rise to what's called graceful degradation. If you lose a few neurons, like you go out and you have a few too many on a Friday night or something, you lose a few thousand neurons. Usually, it's not like all of a sudden you forget what your wallet is or something like that. It's more graceful degradation. You might start to get a little slower in your thinking or whatever, but you don't forget chunks of things generally. And the same thing has been observed in trained neural networks, where in an experiment that I remember is researchers training it to recognize fruits, different kinds of fruits, and then damaging the trained neural network, and then discovering that if they show the neural network a peach, it thinks it's an apple. It doesn't think it's a banana suddenly or something totally different, but maybe it doesn't quite always remember the peach anymore, but it remembers something similar to it. So not just in the terms of the generalization, but people have observed other related effects that are kind of brain-like in some. We've gone way past, and I'm afraid, and Sharon and the folks are looking at me like, what's that? Yeah, maybe if you have any more questions, I'll be happy to stick around. Thanks.